objective.
Signal Integrity Lab was to send a stream of data signals across a long distance and model how that would be affected by parasitics. Basically what we did was take a pseudo-random bit stream and run it through a microcontroller and adjust it through a shift register to model if any parasitics would affect the bit stream, whether it reads 0 or 1 correctly. Alright, so now I'll send it off to Andrew for the theory.
Theory?
Thanks, Guy. Alright, so as Manuel mentioned, we're going to be transmitting these binary digital signals over long distances, and as you all know, there's no such thing as a perfect conductor. So when we transmit over these long distances, we're actually going to have some stray resistance and stray capacitance and inductance as well. These are known as parasitics, and we're going to be interested in how we can model these. To do this, we're going to be using what's called the lumped element analysis. We have a transmitter and a receiver sending out this binary signal, and along the way, we're modeling the resistance, the inductance, and the capacitance in what actually turns out to be a second-order low-pass filter. So once we have this model, we can do some theoretical analysis with it. We're going to try to get the transfer function and see what happens when we pass different frequency binary signals through. So when we get this transfer function, we're looking at the output across the capacitor because the receiver is going to be in parallel with the capacitor, and we get voltage out divided by voltage in, and this is the equation that we end up working with right here. And we're going to make a Bode diagram of this. We're going to pass all low frequencies up to the cutoff frequency. This is a normalized plot here. And after that cutoff frequency, we're going to have about 40 decibels of attenuation per decade of frequencies passed. Now, this doesn't make a whole lot of sense when you look at things straightforward in the binary, because first of all, that's not an entirely periodic signal. This is a random bit stream that can be generated. And second of all, it's not, what is the period of this bit stream? It's hard to say. So what we're actually going to do here is we're going to break down that random signal. We're going to treat it as periodic, and we're going to break it down using a Fourier series into its harmonics. And what this does is it breaks it into a sum of periodic signals at different frequencies. It's all going to be in sines and cosines, as every Fourier series is. And then we're going to go back to this Bode diagram, and any frequency past the cutoff frequency is going to experience a lot of attenuation here. We're basically not going to see it. So what that does is when we're changing from 0 up to 1, then maybe back to 0, or maybe 0 up to 1 and then stay at a 1 for a long time, instead of looking ideal like this where we have 0 all the way up and then like a piecewise function is just going to cut to 1, what it's actually going to do is it's going to round this off, and we'll look at the different ways that capacitance and inductance and resistance can alter this. But what we're working with here is an eye diagram. This is more or less just a zoomed in oscilloscope shot. We turn the persistence up to infinity, layering oscilloscope screenshots on top of one another. When you analyze an eye diagram, there's a lot that goes into it, but in general, you want as wide of an eye as possible. So again, the ideal case is going to be square like this. It's going to be 0, and then in a piecewise fashion, jump all the way up to 1 instantaneously. In the real world, when you have parasitics, you're going to have some curvature to this. It's going to take some time to slope up. You might have some overshoot if you see a lot of inductance in the parasitics. So we're going to take a look at how we can model a long-term transmission and the parasitics that go with it using these eye diagrams and do some analysis.
Procedure. Alright, so for the procedure, you'll need one microcontroller, 16 LEDs, 8 red, 8 green, 16 56 ohm resistors, a shift register used to display the data after the parasitics, several different low-pass filters. You can choose whichever one you want. The data is going to be up to you, and one oscilloscope with 2 leads. So the shift register layout is confusing at first, but I've included a handy chart to make sure you can connect everything easily. So the left side is going to have mostly outputs to LEDs, which will display the data. The right side will mostly have inputs, which will go to the clock, ground, or clock data and latch from the microcontroller, and the 3.3 volts will power the entire shift register. The shift register is designed to take the data and space out the bits so that each bit goes to a different output, allowing us to see the whole bit stream inputted in a series of LEDs. So here's a simple simplification of the microcontroller. It's got all the pins removed except for the necessary ones. You can just follow that to connect everything. And here's the final block diagram for the total circuit. Everything is connected as it should be, and there are a few things that are connected to ground. There are a few things you need to know about the whole circuit. You only need to use one shift register because, as opposed to looking at data from the real world, we actually know and can manipulate what the data is going to be. So we can just take one shift register and see how it compares to the data inputted in the code. So here's our code. It's a little complicated, but the comments explain everything. Right underneath the main statement is how the bit stream is arranged. It's semi-random, so it's not easy to mess up or anything, but we know where an error will be if one appears. And beneath that is the clock counter. The clock counter needs to have twice as many bits as the data stream because it needs to trigger on both the leading and trailing edge of the pulse. The final code just runs the entire system once through and makes sure everything is done and latched when the data is finished transmitting.
Results.
The first circuit examined has the following parasitics: 6.8 ohms, 1 microhenry, and 1 nanofarad. The quality factor is one of the largest ones recorded at 4.65. Due to the low inductance, there is not much overshoot. The second circuit has parasitics of 3.3 ohms, 1 microhenry, and 1 nanofarad. The resistance was halved, being the only thing to change from the previous circuit. Notice that it looks approximately the same, considering the voltage scale is half of what it was, but now the quality control has doubled to 9.6. The third circuit has parasitics of 3.3 ohms, 1 microhenry, and 10 nanofarads. The I is clearly not as prominent, and the quality factor decreased to 3.03. Since increasing the capacitance from 1 to 10 nanofarads was the only change, that must be what affected the I so significantly. For the fourth circuit, inductance remained at 1 microhenry and capacitance went back to 1 nanofarad, but the resistance was increased from 3.3 to 58 ohms. It seems that increasing the resistance to this amount reduced the overshoot. Other than that, it looks approximately the same to the other clean eye diagrams. However, its quality factor is now 0.545. For the final circuit, signal integrity was compromised. The only parasitic to change was capacitance from 1 nanofarad to 20 nanofarads. This large jump in capacitance severely interfered with the signal, giving an indeterminable eye diagram. Its quality factor is now a staggering 0.122. Let's quickly compare the Bode plots of the highest quality control and the compromised eye diagram. Notice the magnitude starts to drop off at about 10 megahertz for the good eye on the left. Now look at the compromised circuit on the right. The magnitude drops off at about 100 kilohertz, which is 100 times smaller compared to the good signal.
Conclusion. It worked! Woo!
So basically, we were able to model the parasitics using a second-order low-pass filter with the resistor, inductor, and capacitor, and see that at certain values for capacitance, the bit stream was distorted, where not every bit was read as correctly as a 1 or a 0. And as for recovery methods, maybe possibly reduce parasitics or have a better algorithm to register the rate at which the bit stream flows.
It's going to be on the quiz tomorrow. Study up.